Hello everyone. In my last lecture, I had discussed what is the Stefan's law, what is the Stefan-Boltzmann law. So, in continuation of that lecture, I will now discuss what is the Newton's law of cooling, what is its application, and how it can be derived from the Stefan's law and Stefan-Boltzmann law. So, first of all, let me discuss what exactly is the Newton's law of cooling. According to this law, when a difference in temperatures of liquid and its surroundings is small, then the rate of loss of heat of the liquid is directly proportional to the difference in temperature of liquid and the surroundings. Let me deduce the Newton's law of cooling from the Stefan's law. The Stefan-Boltzmann law states that if a black body at absolute temperature T is surrounded by another black body at absolute temperature T0, then the inner black body not only loses an amount of energy sigma T4, but also gains an amount of energy sigma T04, where T04 is the temperature, T0 is the temperature of the second black body which surrounds the first black body maintained at temperature T. If the temperature T of a black body is not too great than the temperature T0 of the surrounding black body, we can say that T is equal to T0 plus dt. dt represents a small difference in the temperature. Then from Stefan-Boltzmann law we have E is equal to sigma square brackets T0 plus dt raised to the power 4 minus T0 4. Now let me expand the term in the brackets. So I have E is equal to sigma bracket 4 T0 cube dt plus 6 T0 square dt plus 4 T0 dt cube plus dt4. Thus, the amount of energy E lost per second per unit area of the former is E sigma T4 minus T04. Because dt is very small, its higher order terms may be neglected. Thus, we are left with E is equal to sigma into 4 T0 cube dt, which is equal to 4 times sigma T0 cube T minus T0. So, effectively what we have gained that E is proportional to the difference between T and T0. This result states that for small differences of temperature, the heat loss due to radiation is proportional to the temperature difference between the black body and the surroundings. This is the statement of Newton's law of cooling. So, effectively we have seen that how we can derive the Newton's law of cooling from the simple statement of Stefan's law. Now, before I move on to discuss more laws of black body radiation, let me discuss a few problems in which we have applied the concepts studied so far. So, first example, Earth receives 1400 watt per meter square of radiation. Calculate the pressure exerted by this radiation. What would be the pressure if the radiation is assumed to fall normally on Earth? Here capital E is given as 1400 watts per meter square. For diffuse radiation, we have capital E is equal to 1 by 4 into small u into C. U is the energy density, C is the velocity of light. So, we have small u is equal to 4 into E by C. What is E? E is 1400. What is C? The velocity of light, 3 into 10 to the power 8 meters per second. Substituting and solving, we get small u is equal to 1.87 into 10 to the power minus 5 joules per meter cube. Now check the units. What is small u? Small u is energy density. It means energy per unit volume. So joule is representing the units of energy and meter cube is representing the units of volume. If we take it in the numerator, we get meter minus 3. In my last lecture, I had shown that the pressure of diffuse radiation is given by U by 3. So, P is equal to U by 3. What is U? U is 1.87 into 10 to the power minus 5. Substituting, we get 0.622 into 10 to the power minus 5 Newton per meter square. This was if the radiation is diffuse. What if the radiation is normal? If the radiation is normal, then E is equal to UC. It is not UC by 4. So, we have U is equal to EC, E by C. Substituting, we get U equal to 0.47 into 10 to the power minus 5 joules per meter cube. The pressure of normal radiation is P equal to U. If it is diffuse radiation, it is P equal to U by 3. Now, we are calculating the pressure of normal radiation. So, P is equal to U is equal to 0.47 into 10 to the power minus 5 Newton per meter square. Now, let me discuss second example. The second example is estimate the pressure of radiation in atmosphere inside the sun, treating sun as a black body maintained at a temperature 10 to the power 7 Kelvin. The conversion between atmosphere and Newton per meter square is also given. 1 atmosphere is equal to 1.013 into 10 to the power 5 Newton per meter square. For diffuse radiation, we have pressure is equal to U by 3. So, we have now 4 by 3 E by C, because E is UC by 4. E is what? According to Stephen's law, sigma T4. So, we have now the pressure is equal to 4 by 3 into sigma by C into T raised to the power 4. If we substitute the respective values, we get 4 by 3 into 5.67 into 10 to the power minus 8, which represents the value of sigma, divided by 3 into 10 to the power 8, which represents the value of C, into 10 to the power 7 raised to the power 4, where 10 to the power 7 denotes T, capital T, that is the temperature of the sun. So, just if we simplify this, we get 2.52 into 10 to the power 12 Newton per meter square, or 25 million atmosphere. By million I mean 10 to the power 6. If we have billion, we have 10 to the power 9. Now let me discuss another example. This example says that if we have a wire of length 1 meter and radius 1 millimeter, and it is heated by passing a current through it such that it emits 1 kilowatt of radiant power. Treating the wire as a perfect black body, let us calculate the temperature of this wire. So first we will calculate the surface area of the wire. The surface area of the wire is given by 2 pi RL because the wire is cylindrical in shape. So substituting the relevant values, 2 into 3.14 into 1 into 10 to the power minus 3 into 1. Simplifying this, we get the area of the wire is 6.28 into 10 to the power minus 3 meter square. The power radiated P is given by A into sigma T4. P is the power, A is the area, sigma is the Stephen's constant, T is the temperature. So we have T is equal to P by sigma A raised to the power 1 by 4. So we now get 1 into 10 to the power 3 divided by 5.67 into 10 to the power minus 8 into 6.28 into 10 to the power minus 3 raised to the power 1 by 4. If we simplify this, we get the temperature as 1294 Kelvin, 1294 Kelvin. I hope you have understood this problem. Another problem. At what rate? This is a very important problem and you can see this problem in many exams. At what rate does the radiant energy escape from a hole of radius 1 millimeter in a cavity at 1200 degrees Celsius? So in the beginning we convert the temperature from degree Celsius to Kelvin. Then we calculate the power radiated by the simple formula A into sigma T4. Substituting the appropriate values, we get the power radiated as 0.84 in watts. Another example which is very important, and let me discuss this. How would the energy radiated by sun change if its surface temperature were 10% lower? This is an interesting question, so I thought it is better to discuss it. The sun's surface radiates much like a black body at temperature 5778 Kelvin. By the Stephen's law, we have that the energy of the radiation will be given by sigma into T raised to the power 4. This means since the absolute temperature is occurring in the fourth power, the effect of the radiation is also changed by a factor of 4, that is 0.9 raised to the power 4, which is equal to 0.6561. Hence we have the rate at which the solar energy is radiated and arrives above the Earth's atmosphere would decline by a factor 0.344, which is 35.4% more than the third. So we have discussed a few problems. I have a few more problems, but let me move on to the actual very important problem of Stephen's law we have discussed. Now let me discuss what is meant by the black body spectrum. The black body spectrum was investigated in totality by Lummer and Pringsheim. Very, very important. Lummer and Pringsheim investigated the distribution of energy emitted by a black body at different temperatures. In the subsequent slides, I will show you the experimental setup, and I will also show you what are the important results which Lummer and Pringsheim could investigate and could finally hypothesize by this setup. In this experiment, the black body used is an electrically heated chamber with a small aperture. The temperature of the black body radiation emitted is measured using a thermocouple. The radiation coming out of the slit S1